Welcome back. So we have been looking at recurrence relations and how to solve recurrence relations. So we know what a recurrence relation is. It's a sequence of numbers where we have been given the initial set of values and the nth term is determined as a function of the earlier terms. Recurrence relations is used extensively for various topics in math and other related subjects. We have seen how recurrence relations can be used to model various problems, particularly counting problems, and we have been trying to see how to solve recurrence relations. Now, here are some of the examples that we have looked into, and the question that always comes up is how to solve recurrence relations. So till now we have seen a few techniques of solving recurrence relations. The first one is guess the solution and then prove it using induction. Now if there exists a very nice case, a nice solution, then possibly one can guess it and solve it by induction. Once you guess it correctly, solving it by induction is quite a standard technique. But how do you guess the solution? Now, again, there are some techniques of guessing the solution. The first technique that we looked at was unfolding the definition. Namely, you keep on just unfolding the function, the expression. For example, if Tn equals to 2 plus Tn of n minus 1, you write Tn minus 1 as 2 plus Tn minus 2, and in that case you get Tn equals to 4 plus Tn minus 2, and so on. You keep on doing, and at some point of time you will be able to substitute. After some ith iteration, you will be able to get the thing into a proper form. And we have seen how this technique works and helps us to guess for recurrences like this. But now there are recurrences which are of this form: fn equals to fn minus 1 plus fn minus 2, the Fibonacci number recurrence. And guessing it is complicated because the actual formula is very complicated. And the other kind of stuff that are there is when you have things like bn equals to bn over 2 plus 1, and because of the things like ceiling and floor and so on, it's very hard to get a clean, neat, simple formula for bn. And in that case, there is no guess that can exist. So we saw that in such an example, for example, this mn equals to mn over 2 plus mn over 2 plus n, where the first one is the floor, second one is the ceiling. We, instead of getting the exact solution, can get an upper bound and a lower bound, where the upper and lower bound differ by some constant factor, but that is possibly good enough for us. Sometimes we are happy with a constant multiplication gap between the upper and lower bound. Now, once we have something like this, we would like to say something like mn is actually something like n log n. To formally put it, we basically have to kind of compare these functions, mn versus n log n. And this kind of took us to a different course or different detour of how to compare functions. So how to compare mn with n log n, how to compare n to the power 4 with 2 power n, how to compare n factorial with n power n, and so on and so forth. And what we have seen is that there is this whole thing called an asymptotic notation that helps us to get a hold on how these functions behave. In short, f is equals to big O of g if f is less than constant times g. This is also told that g is equals to big omega of f. If f is big O of g and f is big omega of g, that means if f is upper bounded and lower bounded by some constant time multiples of g, then we say f is theta of g. And we have something like the asymptotic similar notation and the small o notation, which we saw and is extensively used in the literature. So it's very important to know, be very familiar with this set of notations, and it's also very important to know how the various useful functions relate to each other. For example, if you have two polynomials, then if you want to compare them, all that matters is what is the coefficient of the largest degree. What is the largest degree and what is the coefficient? And that helps us to understand how they are related. If the largest degree is same, then they are theta of each other. If the largest degree is same and the coefficient of the largest degree is same, then we have sim of each other. Similarly, we have things like any polynomial is small o of any exponential. Or in other words, as n goes to infinity, any polynomial is way smaller than any exponential function. Similarly, any polynomial of a logarithmic function is small o of any polynomial. So n power square root n, whatever you want to put it. So log n power 20, log n power 30 is equals to small o of square root n. We have things like 2 power n is small o of 3 power n. And we have some other expressions which are used, for which we have some nice, cute expressions which are much more handy. For example, n factorial is asymptotically similar to 2 square root 2 pi n over e by a power n, and so on. Now that we know how to compare functions, and now we have understood, we have got the language of how to write something like mn is close to n log n and so on and so forth. Question is that how do we solve such a function, recurrence? Now the trick for that is, first of all, you have to guess mn for some n. You have to get a feel for it. In the last video, we saw a few more examples of the same kind. The idea is to get a feel for it. So here, for example, if you put n to be power of 2, then you can guess that mn equals to n times 1 plus log n, which basically means it is n log n. And then, instead of trying to solve it exactly, you end up solving mn equals to theta of n log n. And you do it by induction, by first proving an upper bound of mn is less than or equal to constant times n log n, and then proving a lower bound mn is greater than some constant times n log n. Now, we have seen in the last video, there can be quite a number of different expressions, and at least even guessing this term is not necessarily the easiest thing in the world. So what I am going to give you today is what is known as a Master Theorem. It's a theorem that kind of talks a lot about various, takes care of lots of recurrences. So the Master Theorem says that if I have a term which is of the form Tn equals to a times Tn over b plus Fn, where Fn is some function of n, say n squared, n cubed, n log n, 2 power n, and something like that. And if a is greater than or equal to 1 and b is strictly greater than 1, then first case, if Fn is big O of n power c, where c is something less than log a base b, where a and b are these two numbers, then Tn is actually theta of n power log a base b. The second case says that if Fn is n power c times log n power k, and c is exactly equal to log p base a, so log a base b, then Tn equals to n power c log n power k plus 1. Okay. And the third case is that if C is bigger than log A base B and Fn is omega of n power C, then Tn is theta of Fn. So these are three cases. I am not going to prove you those three cases. But again, these are the three cases I would ask you to go and prove it for yourself. They are not hard. Once I state this theorem, you have to just follow the induction technique to solve it. So I will give it as an exercise, solve, or sorry, not solve, rather prove the Master Theorem. It will be useful for you to get a feel of this problem. So this is a very generic theorem for solving it. So instead of solving it, I will see how one can apply Master Theorem to some of the recurrences that arise. The Master Theorem is a bit complicated to figure out what's going on because of this log A base B and so on and so forth. But we will see how one can attack them. So, say here is the first case. So let me just write down here. So it was Tn equals to Atn over B plus Fn, where A was greater than or equal to 1 and B is strictly greater than 1. And what it says is that if Fn is ordered n power C and C is less than log A base B, then Tn is equal to theta of n log A base B. Now look at this example. Tn equals to 8 times n over 2 plus 1000 n square. Now here 8 is equals to A, 2 equals to B, clearly satisfies this expression. It has the same thing as this one, where this number is of course the Fn that we are talking about. And what is log A base B? Log A base B is log 8 base 2, which is 3. And Fn is 1000 n square, which is of course less than n cube. Okay. So, correct? So actually, sorry, I mean this is less than n square, order of n square, and 2 is strictly less than 3. So in fact case 1 fits perfectly, and in that case we can say that Tn equals to theta of n power log A base B, which is 3. So by applying this Master Theorem, we can easily get that Tn equals to theta of n cube. Now this is a theorem, so you don't really have to prove anything once you have a proof of the theorem. But it also helps us to kind of guess what the value of Tn is. In this case, it helps us to understand it is n cube. The second one is of course the case when C equals to log B base A, as a log A base B, and Fn equals to n power C log n power K. Now note that here, what is C? In our expression, if Tn equals to 2 times Tn over 2 plus 10n, C equals to log 2 base 2, which is 1. And clearly Fn, which is 10n, right? this is order of n. I mean, in fact, it has nothing. There is no factor of log. So by doing so, I have satisfied this case 2, and hence what will T of n be? So T of n will be theta of n power c, so it is n, and there is no log here, and therefore I will get one more extra log here, so I get Tn equals to theta n log n. Okay. So again, you can quickly see that we do get Tn equals to theta n log n. Similarly, for the case 3, if when I have this expression Tn equals to n over 2 plus 10n squared. Now here Fn equals to 10n squared. So, and what is C first of all? C is, of course, what is log a base b? Log a base b is 2 by log 2 base 2, which is 1, and 10n squared, which is clearly bigger than, which is n squared, which is, and this is C, so C equals to 2, and 2 is clearly bigger than 1, and therefore what I get is that Tn, from by applying this Master Theorem, I get Tn equals to theta of the Fn, which is n squared. Right? So by just applying this, we get Tn equals to theta n squared. So here is a theorem which helps us to get solutions to some class of recurrences very easily and very simply. But there are some set of recurrences for which this Master Theorem will not work. For example, if I have Tn equals to n times Tn over 2 plus n, this will not work because this a needs to be a constant where this is an n. Or if I have Tn equals to half of Tn over 2 plus n, this will not work because this is a and a needs to be greater than or equal to 1. Or this expression, you can convince yourself that this expression is not something that is satisfied in any of the 3 cases. Or also the other one that we did, which Tn equals to n plus t n over 5 plus t 7n over 10, this is something also doesn't work because it doesn't fit in this form. So, in other words, there are recurrences for which Master Theorem will not work, and in those cases we have to go back to our old method. And there are recurrences for which this Master Theorem will work, and in which case we have a nice easy answer. But there are problems for which all our technique fails. At least the technique that we have seen till now. Namely, what happens if I have this Fibonacci sequence? And how to approach something like a Fibonacci sequence is what we will be doing in the next week's videos. We will be doing something extremely important, which is known as the generative functions. Thank you.